Welcome to the Data Hall YouTube channel. So we have started a series of lectures on panel data analysis. And in these lectures, we are going to cover the theoretical aspect and as well as how do we apply these techniques in statistical packages. So what we are going to cover in these videos is that we are going to understand what is panel data analysis, what is the difference between balanced and unbalanced panel data, and then we are going to discuss the difference between pooled OLS, fixed effect, and random effect. Then there is an important topic of time or year dummy fixed effect or time fixed effect. That is what we are going to also discuss. And lastly, we are going to look into some of the other panel data techniques, that is between estimation, first difference estimation, and within estimation. So let's start our topic. So what is panel data? When the data contains both the time and the space dimension, or we can say that when we have multiple cross sections or multiple time periods in our data, then that data set is called a panel data. So for example, now pooled data or longitudinal data are also a different name of panel data, but there are somewhat different meanings to them also. But for this video, we are going to use them interchangeably. So we are going to consider panel and pooled data as same thing. So for example, over here we have an example of two firms. So we have firm 1 and firm 2. And then we have, for each firm, we have 3 years of data. We have their net income and their total assets. So is this a panel data or not? Now, we have multiple firms and multiple years. So that obviously to our definition is a panel data, because we have multiple cross sections, that is multiple firms, and multiple time periods. So that is multiple years. So that is an example of a panel data. Similarly, if we are working with a country level data, then we have, let's just say, multiple countries and multiple years, and that would also be considered panel data. Or if, let's just say, in this case, we have a longitudinal data where we are measuring the blood pressure of patients before subscribing different medicine and after subscribing different medicines. So these different medicines become different cross sections, and this before and after becomes our time. So hence we have multiple cross sections and multiple time periods. Okay, so what is balanced panel and unbalanced panel? If we look over here, we have two firms, firm 1 and firm 2, and both of these firms have data for all the time periods. So all the entities, when all the entities have the time data for all the time periods, then we call that data as balanced panel data. As opposed to that, we have over here a data set where for firm 1, although we have 3 sets or 3 years of data, but for firm 2, we just have 2 years of data. So what we are trying to say is that when we have different number of time periods for different entities, then that is called an unbalanced panel data. So we are also going to discuss some other topics that would clear our idea when we move towards panel and fixed effect. So we have different types of regressors. We have varying regressor, we have time invariant regressor, and then we have individual invariant regressor. So by regressor, I don't specifically mean, what I mean to say is that there are 3 different and types of variables. So there are variables that vary over time and cross section, right? So for example, production or net income. So this would vary over time and as well as over different firms. So net income would be different for different firms, and as well as it would be different for the different years of the same firm. So we call it a varying variable or varying regressor. Then we have time invariant variable or time invariant regressor that remains same throughout the time period, as the name suggests. It doesn't vary over time. For example, gender or race or ethnicity or color of an individual, or let's just say the geographical location of a firm. So normally within the data, this variable would be time invariant. It wouldn't change over the time. It isn't to say that it won't change, but the idea is that within our data set, it had not changed. So for example, gender can be changed, but within our data set, or location of a firm can be changed, but within our data set, it is a time invariant variable. Then we have an individual invariant variable, which means is that for different individual, it would remain same, but over time, it would change. For example, if we have firm level data, we have different firms from USA, then all those firms would have same inflation for a specific year. So for example, for year 2020, the inflation would be same for all the firms that we have taken from the same country. So inflation would vary over time, but for the same country, it would be an individual or cross-section invariant. Okay, so once we have cleared our idea of different aspects or different terminologies that we are going to use this lecture, let's look into what different techniques we have that we can use for panel data analysis. So we have pooled OLS, then we have fixed effect model, and then when we are using fixed effect for this specific video, what I am referring to is within fixed effect, we have different techniques, but for this video, when I refer to fixed effect, what I am trying to say is that it is a least square dummy variable LSDV method. And what that is, we are going to look into that in further slides. And then we have a random effect model. So there are other models as well. For example, we have between estimation, within group estimation, and first difference estimation, but we are not going to discuss these techniques in this video. For that, we would have a video of its own. So for now, in this video, we are going to discuss three different techniques: pooled OLS, fixed effect, that means LSDV, and then we're going to discuss the random effect model. Okay, so let's start with pooled OLS model, which is the simple model that we had been using for our cross-sectional data. So let's assume that we have stock prices for different firms and different time periods. And what this IT represents is that this I stands for cross-section. So when we have different cross-sections, then we would write I over here. Remember, in cross-sectional data, we do not have T subscript, we just have I. And that means that we have data for different cross-sections. Similarly, this T stands for time period, and that means that we have data for different time periods. So what this IT would represent, if I can rephrase it in plain English, it would mean that we have a data of stock prices for different firms and for different time periods. Similar goes over here. We have ROA for different firm and different time periods. So remember, whenever we have a panel data, we would have an IT subscript. Whenever we have just a time series data, we would have T but not I. And when we have a cross-sectional data, we would just have I subscript. Okay. So when we are using the pooled OLS, there are different firms, right, in our data. We have a panel data. But what we are assuming over here is that there is no individual effect, right? So that's why we would have a same coefficients, regression coefficients for each firm. The slope and the constant would remain same for all firms. And that is what we are saying, is that we do not take into account the individuality of the firms. But if you look at different aspects or different, let's just say this model, we know that there are some unobserved factors that would also impact stock prices. For example, firm culture, organizational culture. These are different time invariant variables, right? Or their geographical location. That is also a time invariant. So for firm's culture do not change within a day. It remains same over time. But at the same time, we cannot observe these variables, right? So we call them unobserved heterogeneity or individual heterogeneity or unobserved firm-specific characters that would have an impact on our dependent variable. So we know from our understanding that if we do not include a variable in a model, where would its effect go into? It would go into the error term. And if the error term and the independent variable are correlated, then we would have a problem of endogeneity, and the regression assumptions says that we should not have endogeneity in our model. So let's elaborate this. What we are trying to say is that, let's just say we have this organization culture. I have included that explicitly in the model. We know that we cannot observe it, and we know that it is a time invariant variable. Let's denote it by alpha I. And why alpha I? Because we know that it does not change over time. Remember, when a variable would change over time, would change over cross section, but not over time, we would assign it an I subscript. Now all those individual factors that we cannot measure and they are time invariant would go into this alpha, and the error term would be basically the composition of this individual heterogeneity and this random error term. So this panel data contains this error term which have both the individual heterogeneity and as well as the random error term. And now let's just say this organization culture, it is quite likely that organization culture would have an impact on stock prices, but that would also have an impact on our ROA. So for example, if the culture is more conducive, then that would translate into a better ROA, a better return on asset. So if that happens, then we have a problem of endogeneity and our estimates would be biased. So one of the issue with pooled OLS is that if the error term, which contains the individual heterogeneity, is correlated with our independent variable, then we have an issue of endogeneity and we do not fulfill the regression assumptions. So one of the way to tackle this issue is what we called a fixed effect model. And remember, when I use the term fixed effect model in our lecture, we are referring to the LSDV approach, least square dummy variable. And why we call it least square dummy variable, let's look into that. And let's look into the idea how this fixed effect model would solve our issue of individual heterogeneity. Now we know that we have this alpha I, which contains the individual heterogeneity, which is the unobserved heterogeneity. What we do is we create a dummy variable for each firm, right? And hence when we include that explicitly into our model, a variable that is explicitly included into our model, then that is excluded from the random error term, right? So what we have done is we have taken these dummy variables, one for each firm. So let's just say if we have 4 firms, then we would create 3 dummy variables, because we know that the omitted category would go into our alpha or beta naught. So we have taken explicitly these dummy variables for each firms, and hence that alpha I had been excluded from the error term, from the composite error term. So we are just left with this random error term, and hence there is no issue of heterogeneity. We can alternatively write this equation as this, where B1I would mean that there is an alpha, a different alpha for each firm. Remember this I subscript. Okay, so because we have used dummy variables to solve this problem of unobserved heterogeneity, that's why this method is called least square dummy variable. Now to further elaborate this idea, let's have this graph over here where we have stock prices on y-axis, which is our dependent variable, and ROA, which is return on asset, on our x-axis, that is our independent variable. And let's let's say we have this data over here, right? This is the actual data that we have. And if we use the pooled OLS regression, the simple OLS regression, then what would happen is that we would have a single constant and a single slope, and we can see from the graphical representation that this OLS is biased in this case. It is not representative of the data. So what we do is, when we create a dummy variable, we have different intercepts for different forms. So for example, for first form, we have a different intercept that would be represented by one dummy, and then for the second form, we would have a different intercept, and that would be represented by a second dummy. So hence now you can see, although the slopes are same for both of these lines, but we have a different intercept, and hence they now represents the data. If we had two firms, as I have depicted over here in this graph, then we would just have a single dummy, and the omitted category would be in the alpha. Or if we have four firms, then we would have three dummy variables, and the omitted category will obviously go into the alpha. Now, this was the basic idea of fixed effect model. We tackle the issue of individual heterogeneity by introducing dummy variables in the model. Now, what are the issues that we face with fixed effect? First, we lose the degree of freedom because we have introduced more dummy variables. The more dummy variables we have, the less degree of freedom we would have. In this case, we just had 4 forms, but you know that in your case, you would have more than that. Secondly, by introducing more dummy variables, there is a chance of introducing multicollinearity in our dataset. But more importantly, the issue with fixed effect is that we cannot, if we have a variable that we want to study, let's just say we want to study the effect of gender on wages, and we are going to use this fixed effect or dummy variable method, LSDV method, then the fixed effect model cannot be used for time invariant regressor. So these time invariant regressor would automatically be dropped from the model. So if we want to study the impact of time invariant variables, then we cannot use fixed effect model. Okay. At the same time, I also want to introduce this idea of time fixed effect. In multiple researches, you would have seen year fixed effect or industry fixed effect or country fixed effect. So what they do is they introduce a different dummy for each year if that is a dummy fixed effect, or different dummy for each industry if that is an industry fixed effect, or different dummy for each country if that is a country fixed effect. So fixed effect means that we introduce a dummy for that specific variable. So a general fixed effect that we have just discussed previously means that we are introducing a dummy for our cross sections, but an year fixed effect or time fixed effect would mean that we are introducing a dummy for each year. If we have 4 years, then we would introduce 3 dummy variables. But more on that when we go towards our Stata lectures, then we would have a demonstration on that, and we would see, we would try different tests and know whether we need to have a time fixed effect or not. Okay, so let's move towards random fixed effect. And we know that we had this model and we had this composite error term that contained both the individual heterogeneity and the random error. And in the fixed effect model, what we did is we excluded this individual heterogeneity by introducing dummy variables explicitly in the model, and hence this was controlled for. Its effect was fixed, right? But for the random effect, we use a different kind of a technique. We use GLS method, but we would not go into the mathematics of that, but we would just look into the intuition of that. We know that the issue is that if there is a covariance between this individual heterogeneity and our independent variable, if that is equal to 0, I mean there is no correlation or covariance between them, then that's fine, we can use random effect. So the assumption of random effect is that there should be no covariance. I mean, if this individual heterogeneity remains within this composite error term, that's fine. But if the issue is if it is correlated with our independent variable. So if there is no correlation with our independent variable, then that's fine. So this is what we are going to check first. This is the assumption of this random effect model. So if there is no correlation between the individual heterogeneity in our independent variable that is equal to 0, then we can safely use random effect model. In case if there is covariance between the individual heterogeneity and the independent variable, that is this covariance is not equal to 0, then we can use fixed effect model. Remember that even if there is no covariance between the individual heterogeneity and the independent variable, even in that case we can use fixed effect model because it doesn't create an issue. So we do not need to create dummy variable. We can create, I mean, if even we create the dummy variable, that won't have an issue. So the idea, but the issue is that with fixed effect, we lose quite a lot of degree of freedom. So there is no advantage of using fixed effect if we can use random effect model. Okay, so should we use OLS, fixed effect, or random effect model? How do we know that? So first thing we need to decide is there a panel effect or not? And that we do using Breusch Pagan test. So if there is no panel effect, that means that there is no individuality or there is no individual characteristics that would impact our dependent variable. Then we can safely use pooled OLS. So is there a panel effect? No, and then we can use pooled OLS. But if there is panel effect, then first we need to do is we need to check the covariance between the regressor, that is our independent variables, and the error term, and that we do using Hausman test. So if there is covariance between the error term and the regressor, then we would have to use the fixed effect. And if there is no covariance between the independent variable and the error term, then we can use random effect model. So that is if covariance is equal to 0. So if I convert that into hypothesis more explicitly, that would give us an idea. First we use the Breusch Pagan test, and the null hypothesis is that there is no panel effect. So hence if the p-value is greater than of this Breusch Pagan test is greater than 0.05, then we cannot reject this null hypothesis and we can use pooled OLS. That is, there is no panel effect. But if the p-value is less than or equal to 0.05, that is, we reject the null hypothesis and we accept the alternate hypothesis, which is that there is panel effect. And hence we would have to use the Hausman test, which where the null hypothesis is that the error term is not correlated with the explanatory variable. And if the p-value of this Hausman test is less than or equal to 0.05, then we reject this null hypothesis, and hence there is a correlation or covariance, and hence we cannot use the random effect models. That's why we would have to use fixed effect model. Alternatively, if p-value is greater than 0.05, so we accept the null hypothesis, that is, it is safe to use the random effect model. So the idea is, if the p-value of Hausman test is greater than 0.05, we can use random effect model. So thanks for watching this video. We would have in our next video we would discuss how to use all these models in Stata, and then we would also discuss the time fixed effect and between effects and within effect and the first different effects. So stay tuned to this channel. Do hit the subscribe button and do hit the like button.